Good morning, everybody. At the very outset, I would like to thank Professor Pradeep for this kind invitation, and obviously the organizers of this conference from Farook College. Uh, Thanks to Rajit for this kind invitation. So over the next 20-25 minutes, I'm going to take you through a very different journey of science. I'm going to discuss to you about molecular crystals, primarily organic entities, and we have been trying to understand properties of molecular crystals. And what has been realized for a long time is that crystals are essentially very rigid building blocks where you have positioning of molecules in the solid state, and this crystalline architecture is held by strong hydrogen bonds, weak intermolecular interactions and other things which actually keep the molecules positioned in well-defined points in space inside the lattice. But what has been realized in the past 2-3 decades is crystals are not just static rigid entities, but they also exhibit dynamics related to motion of molecules in crystals, and these motion of molecules in crystals can be exploited for doing some kind of mechanical work, okay, and or they can be converted into electrical work and so on and so forth. So the dynamics of molecular crystals is very important, and that is where I would like to give you some exposure to this very fascinating field of molecular crystals. Particularly we'll be focusing on piezoresistive sensors, which I will talk to you about later in the talk. So to start with, it is important to look at stability of molecular crystals. When you talk about stability, some of the most important things we would like to expose crystals to are thermal stimuli, for example temperature, optical properties of crystals, that means you can shine light on crystals and see what happens, mechanical stimuli where you apply stress on crystals, exposure to humidity and exposure to pH. So we are looking at solid state phenomena where we have a molecule which is crystallized very well in a solid state architecture, and now we expose it to different kind of stimuli, and then we would like to see the response of molecular crystals. For example, we can look, it has been observed that crystals exhibit different kinds of very complex motions like ballistic motion, bending, coiling, splitting, explosion, shape shifting, which is similar to what we see in case of shape memory alloys, self-healing and creeping. And these properties of dynamic crystals have found applications as sensors in ferroelectrics, optical waveguides, semiconductors, and as well as formulation of drugs, because even a drug goes through the process of tableting where you apply mechanical pressure on the drug and you would like to see whether the phase or the particular form of the drug is retained after the application of pressure. So these mechanical responses or the dynamics of crystals have got a lot of applications, and what is important is to see this particular regime where you start bending the crystal or distorting the crystal, you go into the elastic regime, then you go and finally you have a permanent deformation which is called a plastic regime, and it is important to tune the crystal properties in this elastic to plastic spectrum. So just to give you a few examples of what is mechanical motion in crystals and how this was discovered. This dates back to a nice report in Jackson 2009 when a trans azobenzene compound substituted with a dimethylamino group was exposed to UV light, and these are the crystals you can see, and on exposure to 365 nanometer UV light you see the crystal starts bending, and when you withdraw the light source and apply heat, it comes back to the initial configuration. So this kind of a nice switching of the motion of crystal, when you apply light of a particular wavelength, it bends and then it comes back to the initial configuration when you apply light of a different wavelength. So this kind of cis-trans isomerization property or keto-enol tautomerism has been exploited to see mechanical motion in crystals. And then you can see there are other categories of crystals here. For example, when you are actually seeing that you are applying heat, you can see the splitting of crystals. then you can have movement of crystals, rotation of crystals, explosion of crystals, and you can see displacement of crystals and flipping motion in crystals. So these kind of dynamical effects have also been captured in molecular crystals under the impact of different stimuli. And this has not only been extended to organic crystals, but also to inorganic crystals, for example, zinc benzoate complexes. This was a nice article, first such article reported by Professor Vittal in Angavantha Chemi, where they looked at rolling motion, debris creation and explosion in crystals of zinc benzoate having the ligand which is fluorostyryl-pyridine, because they were trying to understand photocycloaddition processes in crystals where you shine UV light and want to see the cycloaddition process. Instead, they observed that that kind of a process is facilitated by this kind of mechanical dynamic motion. And then Professor Hajime Ito reported a gold complex with chlorobenzonitrile, where again he saw this kind of ballistic motion, jumping, bending and splitting of molecular crystals. Now this is the process where the motion is not controlled. It will be good if you can control the motion and use it to harness it for some particular application. And what was proposed here is, when you have this kind of a motion in crystal, there is some kind of anisotropy. The anisotropy is because you have expansion and contraction along the different directions in the crystal. So you have to see what are the interactions involved in the crystal, and once there is a sufficient build-up of strain after the phase transition, followed by the actuation of crystals. So there is a build-up of a lot of strain inside the crystal, and the strain is released in the form of explosion of crystals, jumping of crystals, displacement of crystals and cracking of crystals in the crystal structure. And this was the hypothesis proposed. Then, keeping these observations in mind, what became very important was also looking at mechanical properties of crystals. And particularly in this regard, I would like to focus for some time on polymorphs here. And what are we exactly doing? So we have here the initial configuration. We have a crystal which has the arrangement of molecules or atoms, and you apply a load. And in case of an elastic crystal, when you withdraw the load, it comes back to the initial configuration. But now when you apply load again, and there is a process of shearing where the displacement of the molecules takes place with respect to different planes, which we call the shearing planes. Then on withdrawal of the load, it is permanently deformed. The final configuration or arrangement is different from the initial configuration. You can see there is a permanent displacement, and this is called a plastic crystal. So, and then obviously once you have a plastic crystal, you go to the region of elasticity and then you hit into the plastic domain. And this one particular example tells you why mechanical properties are important. For example, in paracetamol, when it is being made into a tablet, it was observed that one polymorph has got, the form 2 has got nice tableting properties, but form 1 does not have good tableting properties. So this is when mechanical properties started taking relevance. And to understand the origin of mechanical properties, we need to look at a quantity called the bulk modulus or the Young's modulus of the material. And that is essentially a measure of the resistance to elastic deformation. And then we have got, in addition to elastic modulus, we have got hardness of a material, which is a measure of the plastic deformation of a material. So if you were to look at the role of interactions, which play a very important role in crystalline structures, the strong interactions have a deeper potential energy well, whereas the weak interactions have a relatively flat potential energy well. And the corresponding strong interactions, when you look at the force versus displacement curve, have a highest modulus. That means there is more resistance to deformation when you have strong interactions making the crystal. Whereas when you have weak interactions, they are more susceptible to breakage. You will have a low elastic modulus. So these kind of features were proposed, and this gave rise to the field of structure mechanical property correlation in crystals. And then there were different models which were being proposed, structural models which were being proposed to look at elastic property in crystals. What are the prerequisites for elastic property? And in this regard, you look at this crystal, as you see, this is the arrangement of molecules, and now you are elastically deforming the crystal. So in case of elastic deformation, it is reversible in nature. There is interlocking of molecules such that they don't permanently slip across each other, and there is permanent deformation. There is a structural buffer which kind of restores the initial configuration. and the inner arc is shorter in length than the outer arc. So the outer arc deforms, the inner arc is contracted, and the middle layer is the undisturbed layer of molecules. This is what was proposed for the expansion compression model in the case of elastic deformation. Contrary to that, the plastic deformation is characterized with columnar packing, and there are anisotropic interactions. So one direction you have very strong interactions, in other directions you have very weak interactions, and that is what facilitates promotion of molecules, movement of molecules along the weak interactions. You can displace molecules when you have weak interactions, but you cannot break the strong interactions. So the molecules in one layer are held by strong interactions, in the other directions are held by weak interactions, so that gives rise to the plastic deformation, and you have this irreversible migration of molecules, and during this process, unlike the elastic deformation where there are changes in distances, there are no changes in distances between the molecules in the column and across the molecules between the columns. So this is one notable geometrical feature in plastic deformation. These two models have been proposed after observing a large number of mechanically deformed crystals. So these are like guidelines or hypotheses for elastic or plastic deformation. So now you can see this is the very first interesting case, I would like to say very interesting case, where elastic co-crystals of caffeine and chloronitrobenzoic acid were grown in the laboratory. This work was done by Professor Malla way back in 2012. And you can see these are long needle-like crystals, and you apply stress on the major face. So in a crystal you have got major faces and minor faces, and we do these kind of 3-point bending experiments where you take a pair of forceps, and then with another pair of forceps you can actually try to apply stress on one side of the crystal, and you see that you are able to bend the crystal in a circular way. Normally organic crystals are brittle, they would have cracked by now. If you apply a little bit of stress, they will simply crack. That is the brittle nature of crystals. But in this case, we were able to get nice, in this report they were able to get nice co-crystals, nice bending crystals, and when you withdraw the stress, they come back to the initial shape. And this is, as I told you, in case of elastic bending, there is a change in length, the outer is longer than the inner, whereas in case of plastic bending, the lengths remain the same. However, these angles between the, this angle theta undergoes change in plastic bending compared to elastic bending, where it remains same compared to the initial unbent crystal. And to see that feature, whether this changes, you can look at the ends of the crystal in elastic bending, and you will see that there is practically no change in the angle between the faces. And then what we do is that we do a single crystal X-ray diffraction experiment to see whether the crystallinity of the crystal is maintained, whether the crystallinity is retained, or whether there is a change in the structure at the bent region. So we actually have the loop, and we have this bent crystal which you lock it using this loop, and now you shine X-rays at the bent region. This is the bent region, and compare it with the crystal in the unbent region. You will see that the peaks are very, very sharp, and here you see that there is diffusiveness, there are streaks, and therefore the peaks tend to get broadened. But again it comes back to this positioning, the initial configuration, you again restore the crystallinity of the material. So that tells you there is some kind of mosaicity or spread, there is broadness of peaks when you bend the crystal in the bent region compared to that of the unbent region. So these kind of observations are proposed to look at what happens to a crystal in the bent region compared to the unbent region. And the elastic property was proposed due to this interlock structure. You can see this is the interlock structure. So when you have the interlock structure and you apply stress, then these layers will actually bend, but they will not buckle completely, because this interlocking prevents the permanent migration of molecules. If this interlocking had not happened, or interdigitation had not happened, then the molecules would have simply moved past each other, and that would have led to plastic deformation. So this interlocking of the molecules, where you can clearly see this is a solvate, and this is your caffeine, and this is your chloronitrobenzoic acid, they are nicely arranged in this co-crystal. This structural buffer is important to retain the elasticity of a crystal. So then the next question was that, okay, we have a model for elastic crystals. Can we get a structural model for plastic crystals? So we were also looking at this feature in our lab, and in this particular compound you can see this is a ethanol substituted fluoro-trifluoromethyl benzamide. We were able to grow long acicular crystals of this compound, and when we did the 3-point bending experiment, you can see we were able to deform the crystal deforms. And interestingly, this deformation propagates along the entire length of the crystal. So you can apply a stress, tangential stress at the ends of the crystal, and you can actually see the deformation or the bend shape propagation along the entire length of the crystal. And then we were also able to restore the shape restoration. Normally if you have plastic deformation, you cannot restore the original configuration, but in this case we were able to recover the original shape. And obviously there is some loss in crystallinity during this process, but overall shape restoration is very important. And you see, we were able to write this ICER Bhopal with crystals of different sizes, and we were able to distort it into different shapes. So you are able to plastically deform this crystal the way you want and mold it the way you want, and again bring it back to the initial arrangement or the initial configuration. And so we take this particular representation where the major phase, as you can see, this is the major phase, is the bending phase. And we also did the TEM imaging to show that at this region, the cross-sectional area where you have the bent region, there is some pile-up of defects. There are defects which are created at the bent region. So we were interested to now see whether at the bent region these defects alter the structure of the material at the bent region. And in that regard, we planned very advanced experiments. We did two sets of experiments. One is that we did nano indentation, where we look at the modulus values at the bent region compared to the unbent region. So you can see these are the nano indentation responses, and you can see that the indentation modulus at the bent region 1 is very low compared to the unbent region, and the same is for the hardness. So that tells you that your mechanical property is modified at the bent region, where the material becomes very soft compared to that of the unbent region. And now we do very advanced microfocus experiments at the synchrotron, where we shine X-rays along the entire region of the bent crystal. We start from here and we move 5 micrometer at every distance of the crystal, and we are able to collect data, and we are able to see that for 30 positions, around 30 experiments we did around the entire bent region of the crystal, we were able to see that the lattice parameters practically remain the same. That tells you that the crystal structure at the bent region does not get affected by this bending deformation. And when you also have the restoration of the shape, that is also a very key feature. Only you see that there is some broadness in the peaks, but overall the structure remains the same. So this you can only do by very advanced experiments where you shine X-rays at every region of this crystal and see that the structural integrity is maintained. And now we would like to understand, because we are chemists, we would like to understand what is the role of the packing in facilitating this plastic deformation. And here you can see that you have this columnar packing. You can see the bilayers here. You can see these bilayers. This is the organic part. This is the CF3 part. So when you are applying stress on the 100 region, these CF3 functional groups act as rollers. So the molecule, the sheets are able, the layers are able to move, and that rolling motion is facilitated by the CF3 groups. So CF3 contacts here play a very important role in roller-like motion. But beyond a certain movement, the ethynyl groups which are sterically bulky, they clash. So that steric clash prevents the irreversible migration of these molecules, and that is the reason why you can have the shape restoration property in this particular way. So this kind of validates the slip plane model, which is the anisotropic model, which says that you have strong interactions in one direction and weak interactions in the other directions. But here it is purely by CF3 contacts we were able to achieve this nice rolling motion in molecules in the crystal, and this is what we propose. So if you take, for example, A4 sheets of paper rim, and you simply, simply twist it a bit, you will see it's like a seam of this rim of A4 size paper, where you see this kind of a change in angle at the bent region, and you have nice rolling of these molecules across the CF3 layers in either direction. And this slippage is very, very comfortable because of the CF3 groups. In absence of CF3 groups, this does not take place. So this study validates the plastic model for crystals, that you can have molecular migration because of the CF3 roller functional groups. So now with all this background, the next question I ask is that, what do I do? I have plastic crystals, I have elastic crystals. Can I use it for some application, which I would like to demonstrate in the next 10 minutes. So we have taken this particular crystal CF3NCS, okay, and this is not a very stable molecule, but its melting point is low. But now we see very interesting coiling behavior. We get these long crystals, and when we apply stress, we see the nice coiling behavior of these crystals. You have twisting of the crystals, and then you are able to coil these crystals into nice loops. You can see this is a two-dimensional representation of the loop. So you're able to make nice coil-like structure of these molecules. And you can again see that this is the TEM image, and under the beam of electrons there is some damage here. We did similar experiments to again show that deformation at the bent region is less than 1%. And we did the nano indentation experiments on the major faces, the 001 and the 101. Again, it shows that the hardness changes as a function of the crystal phase. And what is important is that what is the mechanism for plastic deformation I would like to illustrate. So you see here, this is the packing of the molecules. See it very clearly. Now this is the slip plane. This is the slip plane along which molecules can move either towards you, b-axis, or they can move along this particular plane. So now when you have two forces, one like this and one like this, that is a tangential kind of a thing, then you will have called helical motion. You will have helical twisting. If you were to have only longitudinal deformation, there is only one direction of stress. But when you have a perpendicular direction, then the coiling motion starts, the twisting motion starts, and that is what observed here. You can have, when you indent it here, you can have movement towards you, and you can have also movement perpendicular to that direction, and that is the origin of the coiling motion. And the energetics are important. You disrupt around 60 kilojoule mole energy here, whereas it is around 42 here. So you disrupt these interactions, and that facilitates the coiling motion. And when you do that, this molecule has got a SCN group, and the SCN group can actually change its conformation without much change in the energy. So the energy penalty to change the conformation is less, and that is why you can have this slippage of molecules where the SCN groups move past each other. And you can see here that we are able, this is what accounts for the coiling behavior in case of molecules. You can see this nice twist as I explained. And now we were interested to know a very important property called piezoresistive property. This is very important in wearable electronics and sensor devices which find biomedical applications. So some of the most important parameters are sensitivity, detection range, linearity, response time, and cyclic stability. And essentially this is the change in resistance with the change in pressure. So we devised two types of sensors. One is we have it with the P-dot PSS, and the other is with my organic crystal. And this is the response as a function of pressure, where you can see there is some kind of instability associated with the sensor. This is the device, the sensor which has been made. This is the PDMS substrate. This is the microchannel into which you put your sensor, and you complete it with the aluminum electrode. And as you can see, compared to sensor A, sensor B has got much better sensitivity, which is reproduced here. And we did it over 4 batches, and we were able to see that the deviation from the mean is very less for the, this is at 30 kilopascal for the sensor B. So this is the microchannel. This is the actual device. This is the 520 micrometer microchannel into which you put your material. Now when you compress it, you can see that there is a decrease in cross-sectional area. And you all know if the cross-sectional area decreases, the resistance increases. So you can see that this is the data for my sensor B with my molecular crystal. You can see this is very, very nice response. Stability is there, and there are continuous increase in resistance, and there is a switch over at high pressure. So there is a low pressure regime, there is a high pressure regime, and we are able to see nice sensitivity in this region around 0.08 kilopascal and 0.22 kilopascal inverse. We are able to cyclize, we are able to do this at will around 100 cycles, and the loading unloading time response is also very, very least, which is very important for a sensor as to how fast it responds to an applied pressure. So you can see this is the performance for sensor A without my organic material. And with my organic material, this is the data. So what my organic material has done, my organic material has a much better response, has a much improved response compared to the sensor A, which is without the organic crystal, because it provides better mechanical compliance because of the mechanical deformation it has with it. So it can accommodate the stress much better, leading to an improved response. And we have compared this with the reported values in the literature for composites, for layered structures, for graphene coated forms, and also for porous PDMS substrates, where the data is given to you. So the performance of a sensor is appreciable. This is the first example of a molecular crystal as a piezoresistive sensor. And we have now extended this studies to other things, and this is the latest data. I will kind of summarize it here. We are trying to analyze this further. These are the performance of the sensors. I don't know whether this will play. I just wanted to show you this video, 1 minute, 30 seconds. I don't know whether it will play or not. I think it got locked here. Okay, it's playing actually. You can see this is you are applying the pressure here, and you can see the response of the sensor. So you have the response, the piezoresistive response being measured over more than 100 cycles. So you can see the application, withdrawal, and the pressure is increased. So with this, I would like to end my presentation. Well, there are many examples we have of plastic crystals. We are looking into those in benzamides. And with this, I would like to end. Acknowledge all the funding agencies and my collaborators, Dr. Mitradeep in electrical engineering, Professor Clegg, and Dr. S.R. Mangalapalli for the indentation experiments, and obviously all the students who have worked on this project. Thank you very much for your attention.
Thank you, sir. Thank you, sir, for finishing the talk in time. And you have actually taken us to a beautiful world of molecular crystal and the application, its plastic and elastic deformation, and how this can be applied to piezoresistive sensor. Now, thank you once again. And now the session is open for discussion.
As I was, Deepak, very nice. As I was hearing you, I was thinking, what is that computational science can do in specifically understanding the extent of molecular changes that are involved? And is it a priori predict the right kind of crystal system wherein you can go back and then crystallize them?
Yes. So there is one very recent report in chemical science where Professor Sharmake, he's a computational materials chemist. He has first predicted the value from nano indentation value, and then they've gone and prepared the crystal and exactly experimentally got that nano indentation value, and then looked at the origin of plastic response. So people are now trying to work in the reverse direction, predict modulus values, predict the elastic constants using simulations, because these elastic constants are tensors, and you can have CIJKL, you can have a 4-rank tensor, 4, 3, 2, depending on the nature of deformation. So they're computing these elastic constants, calculating the bulk modulus value, and then seeing whether the experiment nano indentation actually reproduces this value, and then go to the packing and see that what is the origin of mechanical deformation, rather than working in a trial and error method. So there has been some progress already, and people are working at it.
So the second thing that I was looking at or thinking about was something larger in the context of avalanches.
Mm-hmm.
So if you start thinking about ice undergoing deformation, an early prediction of that is very important.
Yes, yes. Natural processes,
right. And
those are large-scale processes.
Correct. And the second aspect around the same thing is to extract energy from that.
Yes, I agree.
So from both these directions, I was thinking as to how your studies could be related to something large scale.
I think that is where we need geochemists and, who are working on, or earth scientists who are working on understanding how rock migration happens and how do these plates move. And I have been attending some of these as examiners, as external examiner for these kind of things. So there they have bigger questions. Why do these plates move? What is the origin of plate movement, tectonic movements, magnitudes of this, and what is the mechanical hardness of rocks? What is the nature of this? That's a fairly complex multi-scale simulation project. And they are also trying to understand these things.
In a related context is construction.
Construction, yeah. Okay.
Buildings and bridges and things like that.
Yes, so that is a bulk property. Yes, right. Yes, definitely.
Where understanding deformation with an embedded object of this kind, whatever molecular or otherwise object of this kind, can spontaneously, inform, or a real-time sensor is put in there.
Yes, that is, yes.
Right.
That is the ultimate objective.
I was thinking of the directions of your research.
So currently, yes, this is I'm very happy this is the first report on piezoresistive sensor for a molecular crystal. These are important in wearable electronics, which has been very, very popular. And my friend who is working in electrical engineering, he's actually been designing sensors for wearable electronics. So this is a very potential system which will give more stability and more impact. That's what he says. But definitely there is scope for improvement on a larger scale. We need to explore that, sir. Thank you for input.
Very nice, Sir Deepak.
Thank you, sir.
I had one doubt. When you bend the crystal, and in the bend region, you say that on one hand you have the same unit cell.
Yes.
And on the other hand, you show that nano indentation results,
Correct.
the stiffness has gone down really high. Now, these two are counterintuitive.
Yes, absolutely.
And the third point is that when you see the bend, you already see that crystal has elongated 2 to 3 times.
Yes.
So how do you get the same?
So that's a very, very valid question. So every experimental technique has some potential and some limitations. But so definitely in the bent region, the modulus has decreased. There is a pile-up of defects. There is a lot of defects which have piled up. So defects are intrinsic. But when you do X-ray diffraction experiments, you are even going lower or higher in resolution. In the atomic scale, you are going lower and you are going higher in resolution. So you are trying to do, because now, okay, this experiment is being done by moving the X-ray beam 5 micrometer. Very, very tiny displacements. And the nanomechanical measurements are at bulk, at that level are maybe much longer distances. So say whatever defects you are creating, lower than that, whatever structural rearrangements happening, they are still retaining the structural integrity. We are not able to capture the operational or defects on the crystal structure. Although the defect concentration is high, but it is not yet so high that these kind of very, very sophisticated mapping at very, very atomistic level, this is at atomistic level, whereas that is at that displacement is micrometer, this is at nanometer angstrom. Okay, so we are still probing more deeper, and at that level, the structure is still maintained. There is some deformation within, so this within 1% is good, very good data. Beyond 1%, they say your structure would have changed.
Okay. And the second question is, you showed in the first part that you showed 2 tablets, I guess.
Yes, paracetamol.
And you also talked about mechanical properties.
Yes.
But it also looked like that when you talk about this one, it is not the crystal, it is also the grain boundaries.
Those are there, but the idea is to see whether these grain boundaries are present or how much they operate. But normally it has been attributed to this kind of a model where the nature of interactions is different in 2 different polymers, and that kind of decides the hardness property and the ability to withstand mechanical pressure. But to start with, grain boundaries is something is a very important concept in metals and oxides, but not really been explored here. We need to still look at grain boundaries and all. Yes. But most of the time it is attributed to the packing, that the nature of the packing is what decides the mechanical properties of the particular polymer. That is how the subject has evolved in the last 2 decades.
Hi Deepak, very exciting talk. Yeah. So my point is related to the molecular structure, because it's all dependent on the structure that you choose. So,
Absolutely.
my first question is, how do you get the intuition to have such a structure to have the bending? Because when we talk about crystals, we always think of having an ordered arrangement which don't deform.
Yes.
So how did you reach to this structure, especially you have that CFT group which is
So,
playing a
yes.
significant role?
So
Or it's
definitely,
a trial and error. That
no. These are all very high quality structure determinations. So I'll tell you the difference. I'll tell you. So now when you do these experiments, there are 30 experiments we did over at different points. These structures are having loss of crystallinity. There is some mosaicity. So we are not able to refine the structures to complete an isotropic thermal displacement parameter. We are only able to do at isotropic level. So there is a certain loss in the integrity of the structure. But there is no displacement of the molecules. Like the plastic model I told you, there is no changes in distance between the molecules as well as across the molecules in different columns. That hypothesis stays valid. But yes, at the level of refinement, what you will achieve in a routine, this unbent region, what will it will have? The bent region will afford less accuracy. But yes, the structure is still there. Now you see this, this structure is from whether the bent region or you have an unbent region, the structure is the same. Now what facilitates is this rollers, CF3 rollers, to accomplish this particular gliding motion. And this is the first report where CF3 has been explored to achieve this kind of migration of molecules. See, CF3 is very important in fluorine, is very important in drugs and pharmaceuticals. But it's the first application of CF3, lower functional groups, to achieve this kind of shape restoration, plastic deformation in crystals. Because these are weak contacts, these are very weak contacts. You can explore it. So you can actually not do it a priori, because you first see the observation and then try to see what is the origin of it at the structure level.
Quite interesting to discuss.
Thank you.
Thank you.
Thank you. You have one more.
Deepak, excellent talk. One quick question. I could see that there are two different sensitivities when it comes to the application of pressure.
Yes.
Has that been an operational hazard when you are using a piezoresistive sensor?
Yes. So it depends on the nature of application. For example, when these wearable stuff is used for detection of pulses in heart and hair and all, it depends on the range of pressure. Some processes take higher pressure, some processes take lower pressure. But what is interesting for a sensor, you have a very smooth increase in sensitivity as a function of pressure. Normally they are abrupt discontinuities, and also when you withdraw the pressure, whether the device comes back to the initial state. So if you look at this one, which is without my material, it's not a reversible process. It is a discontinuous process with instability. I'm not able to get data points across the entire spectrum of pressure. Now I create that stability by putting this mechanically compliant crystal which accommodates the pressure which is being applied on the sensor to monitor the electrical responses more accurately. Because you are monitoring it using this sigma, which is the conductivity, and the reciprocal of this is the resistance. So these tiny changes are being well monitored because of the fact that the pressure is well being taken by the molecular crystals. Without that, it is like this. But in the high pressure regime, it becomes okay. But here it's more continuous and then it kind of stabilizes. Yes, there is a change in resistivity, sensitivity, but definitely it is very accurate. So you can actually monitor it very, very well. There's no problem with that. And the challenge is to do for high pressure rather than low pressure ranges.
Now it's already time. Okay, one more question. Yeah. Only one question.
Hello. Could you please tell me how these dynamic crystals are useful in optical waveguides?
So optical waveguides, Professor Rajudarai Chandrasekhar at University of Hyderabad, you can check his literature. He has published a lot of work. So basically the first requirement is that you have got hollow crystals and you send in light, and then you monitor the movement of light, and you now see light coming out at the other end of the crystal. There is decay in the intensity of the crystal. There is di by I, there is optical loss, and lower is the optical loss, better is the transmission of this light from one end to the other. And it has been observed this loss is very, very low if you have hollow crystals which allow propagation of light. And if you have bent crystals also, but they are hollow, you can have propagation of light. So this property of propagation of light is what is important in optical waveguides, essentially.
Thank you.
And you can make circuits by these bent crystals. You can make tiny circuits. If you have a long crystal like this, you need more space. If you are able to bend it and coil it and study the same property in less volume, you can achieve more performance. So that is the basic underlying principle of optical waveguide.
Because of time constraint, we can stop the discussion right now and continue during tea break. Now we can thank the speaker once again. And now I humbly request Professor Deepak to receive a token of appreciation from our side. Please, sir.